Good morning everyone. Today we are going to discuss the PID control and application to DC motor. So this is the supplementary file 2 for the video recording. So this is the supplementary file for the lecture number 2. This is a part of 1 week online unique hands-on student development program on control system design from a beginner to an expert, SDP 1.0. And myself is P. Bharani Chandra Kumar, and I am an academic at GMRIT of Technology, Rajam. Sorry. So we have already discussed and we have derived the transfer function as well as state space model for the DC motor, and this is the reference from where we have considered this particular plant. So this is very much important, which we are going to implement, and this ABCD matrices are also important. So the plant parameters with appropriate units has been selected something like this. However, this is more important: design specification. The settling time should be less than 0.5 seconds, and peak overshoot should be less than 5%, and the steady state error should be less than 1%. So these are the desired specification which we have selected. First of all, we have to create the parameter file. The parameters have JBKRL. This is the plant parameters, and these are the state space matrices. D equal to 0 2 times it has been typed. You can delete one. If you are not deleting also, it is not going to change because D is 0 in both the cases. So where to type this file? What you have to do is go here and new, create this new, and it will open a new file. Copy and paste all the parameter values there and the ABCD matrices, which I have done here. If I run this one, so all the corresponding J, B, K, R, L, ABCD matrices, which will be in the workspace now. So this is the first part, and the second part, what you have to do here is you have to develop the open loop model. So this is the plant model. So you have already seen this open loop model in our earlier lectures as well. So however, the important thing to note here is that this plant is a DC motor model and this is a state space model, which is something new to you. So how to get this one, I will show you. So this is the open loop model. So this is the same transfer function what we have seen here. However, interestingly, you can see that this numerator is k, that's why I kept as a k, and the coefficient of s square is j into l, gr plus bl, so rj plus bl, because they are scalar, so it doesn't matter if you interchange both of them. And the last term is the constant term is k square plus b into r, k square plus r into b. So this is the one what we have seen, what you can see it now here. And the thing what is not known to us is this state space matrix. So how to get the state space matrix is click this Simulink browser, and in the continuous this is the state space matrix. Right click and add here. So by default it will have 1 1 1 1 and 0. So these things you have to change it. So this need to be A, B and C, D matrices, A, B, C and D matrices. Since already in the parameter file we ran the parameter file, this A, B and C and D are already in the workspace. So from the workspace this block will import that one. And now I am going to run this one and I will see what is happening. If I run, you can see that this is the one, this is the response. The first and most important thing from this plot, you can see that the steady state error is there is 90% steady state error because of because it need to settle at 1, but it is settling at 0.1. So that tells us that we need some kind of control strategy for this one. So this is what we have seen here. You can plot the same thing what the small tiny code, you'll get the response like this. And this is the unit step or with a step time 0, so that is a constant, and both the outputs will be the same. I will show you both the outputs. You can see that this is the same, it is, and this should also be the same. These two are the same because the transfer function or the state space is just the different representation of the same system. So that's why the output should not be output will be the same for both the cases. So since the steady state error is 90%, so we will now use the PID controller design to see what is happening. For the PID controller design, so this is the PID controller. You can see that this DC motor transfer function, the same thing what we have seen is the same thing. However, I have just compressed it as far as the size is concerned because it is too big. This is the PID controller. We will see how to do this one. So I have already generated here this is the same transfer function what we have seen, k by js square and auto, and just I have shrinked it, and this is the PID controller. So PID you can obtain from here. You can see that PID, if you just type PID, it will come back here, and you just add to the block. I'm removing this old PID. I'm doing from the scratch this PID design. I just connected this PID design, the PID block. And now the thing is how to find this PID values. So earlier in the lecture just we have kept some random values, or we have tuned manually. I will tell you how to tune this automatically. This is very much important. So once this is ready, just save this with some name, and double click this one. By default it will have 1 1 and 0 kp ki kd values. Just press this tune button. It will take some time, maybe half a minute, based upon the speed of your processor and so on. So you can see this is the one. So you can see that this is the blocked one. So if I use 1 1 0, I'll be getting this dotted one, and this is the tuned one. Tuned one means with different PID values. So to see what is happening there, what you do here is you show parameters, and there are two slide bars here, gain sliding bars. So one is for the response time and one is for the transient behavior. If you want the faster response, you can see what is going to happen. And this is the dynamic, this is the dynamic GUI. As soon as if I change this one, the corresponding PIP, KP, KI, KD values, it is going to change. You can see that the system is, I want the settling time to should be less than 0.5. The first parameter is that is of interest. So I will make the system more faster. So now settling time is 0.451. This is less than 0.5 seconds. So that is very good. But the overshoot is large. Overshoot is around 10. So what I will do here is this particular gain. So I will not go for the aggressive one. I will just keep on changing. And now at some particular time, now you can see that now the overshoot is 4.23, and the settling time has increased because we want 0.5. So what I will do is I will make little bit faster this one. Now you can see the all specifications are good. So 0.475, which is less than 0.5 second is the settling time, and the overshoot is 3.5, or overshoot is 4, approximately, let's say 3.6 or so, which is less than 5%. So our desired specification has been set, and these are the corresponding KP, KI, KD values, and this is the n, which this n is the filter parameter for the derivative gain approximation. So what I'm going to do here is you don't have to this is the tuned value. So if I substitute this, you should able to get the desired response. So what I'm going to do here is, instead of directly typing this in the PID block, I will just click this update block. As soon as I click the update block, in the block all the parameters will be updated. I have to click OK, and now I'm going to run this one. This ran, and you can see the very nice plot. You can see that it is settling what we have seen there. The settling time is quite less, 0.4, and the overshoot is less than 5. So if you want to see how it is happening, you can just zoom. You can, okay, so I think it got stuck, but that's fine. You can see that it is, now you can see this one, and I will take the y bar. This is the maximum value. You can see that it is, around 3.59 what we have seen. 3.59, approximately 3.6 is the peak overshoot, and the settling time is also less than 0.5, and the steady state error is almost 0, because okay, some GUI issue, but that is fine. Steady state error is also 0 if you run it again. So you could able to see that one. I will be running this again. You can see that steady state error is almost 0. There is no almost my output has almost reached to 1. So this is one such design. There are infinite possibilities of kpk kd values, and if I zoom for this one set of kpk kd values, you can see that less than 0.5 second it is settled, and the overshoot is also very less, and the settling time is also the steady state error is also 0. So this is the large in the time scale 0 to 10. If I have taken only the time scale till 1, so this will give a more clear picture. And this is the such comparison, open loop and the closed loop. Open loop, you can see that rise time is greater than 1, peak overshoot is 0, and settling time is 2.5. It is taking almost 2.5 seconds approximately. And the important thing which is the steady state error is 90. We don't want the steady state error, but when I use the PID controller, the rise time is 0.06, and peak overshoot is approximately 4, and settling time is 0.4. So the design what we have done, and this might be little bit slightly difference, but it doesn't matter because it has met the desired specifications. So there are infinite number of PID gains possible, so it doesn't mean that only one set of PID gain will always give you the desired response. There are thousands or millions of combinations possible, and they are not unique. So thank you very much. Thank you for listening. Thank you. Good morning everyone. Today